in our video for today, we will discuss about the moment about a point. Now, in physics and engineering, the moment about a point is a measure of the tendency of a force to rotate an object about that point. The moment m about a point is calculated using the formula m is equal to F times d, where F is the applied force and then d is the moment arm, or the perpendicular distance between the force and the point. Now what you have to remember here is the moment arm is always the perpendicular distance. Now what this means is that you will always consider a line that forms a 90-degree angle with your force. And so if you have a force like this one, and then let's say you have this line, and then you are taking moments about this point, and then let's say this is F, this will be your perpendicular distance. Now this is because our force F forms a 90-degree angle with this line. Now let's say you have a force like this one, and then you are taking moments about this point. Now, your moment arm will not be this distance, because as you can notice, this isn't perpendicular to our force F. What's perpendicular to our force F is this line, because this is a 90-degree angle. And so this will be our D, because this is the perpendicular distance. Now, in order to internalize this one, let's try to solve an example. Now, we have this cross-section, and then let's try to solve the moment about a point. And so we will just actually move this one. Now, we must first recall that we can move any force along its line of action, and then it won't change anything. Like for example, this 20 kN load acts along this line, and so you can move this anywhere. You can move it here, here, or even here. Now let's see that in action. So you can actually move the 20 kN load right at the bottom. Now it will look like this, and then this won't change a thing because it's still along its line of action. So this is what you have to remember. And then similarly, you can also move the 10 kN load at this point, because this is still along the line of action of this particular force. And so it will depend on you whether what you find convenient. However, let's just stick to this one. And then notice that we have an inclined load. Now it will be difficult to find the perpendicular distance about any point if we have an inclined load, because let's say you want to take points about point A, and so you must draw a parallel line to this load. So you have this parallel line, and then notice that this will be your perpendicular distance. Let's say this is D, and then this is a 90-degree angle. Notice that it will be difficult to solve D because you have to apply geometry. Again, this is our D because this is the perpendicular distance between this load and point A. Now this is just an example. Now sir, how are we going to make this easier? We can make this easier by resolving the 50 kN load into components. Because if we have an inclined load, it will be easier to identify the perpendicular distance if we break it down into horizontal and vertical components. And so let's try to do that. And so let's first try to isolate this load. So let's just move that here. This is our 50 kN load. And then notice that since this is inclined, it will have a corresponding vertical and horizontal component. Now let's say that this is the vertical component, and then this is our horizontal component. Now sir, what will be this force? We can actually reduce this one into a triangle with our inclined load as the hypotenuse. So we will actually form this triangle. Now this is 30 degrees, and then our hypotenuse will be 50. And then we have the y component of 50, and we also have the x component. Now sir, what will be the y component of 50? To get y, we will just use the sine function, because again, we have SOHCAHTOA. This means that sine is to opposite over hypotenuse. So sine theta is equal to opposite over hypotenuse. Now our opposite side is y, because this is opposite to our reference angle. Again, this is opposite and this is adjacent. And so we have sine 30 is equal to y divided by the hypotenuse. And so our y will become 50 sine 30, which will become 25 kN. And so this is actually 25. And then sir, how about the horizontal component? For the horizontal component, we will actually use cosine theta, or the cosine function. So we have cos theta is equal to adjacent over hypotenuse. Now our adjacent side is x. So we have cos 30 is equal to x divided by the hypotenuse, which is 50. So we have 50, and so our x will become 50 cosine 30. And so our x will be 43.3. And so this is actually 43.3 kilonewtons. And so now, since we have resolved this into its components, we will just actually use the components. And so if we want to see that in action, it will look like this. Instead of the 50 kN load, we will just actually write this one in order to make our calculations easier. So let's just erase this one, and then let's try to solve the moment about A. Now let's first define our sign convention. Now counterclockwise moments or moments that cause a counterclockwise rotation, that will be negative. And then moments that cause a clockwise rotation, that will be positive. And so this will be our sign convention for the purposes of discussion. So let me just erase this one. Let's first calculate this one. What is the moment about A? Now this is our point A. Now when I was still a student, I would always think that the point I'm taking moments about is the part of the section that I'm holding. And so for example, if we want to calculate the moment about A, let's try to imagine that we are holding that point. And so let's say we have this one. So try to imagine that you are holding point A. And then let's try to first consider the rotation caused by the 20 kN load. And so let me just highlight this one. Now notice that if you hold this point and then you apply an upward force right here, our object will rotate counterclockwise. And then if you want to see that in action, it will look like this. Again, this is the original point, and then it will actually rotate counterclockwise. And so if we are to calculate the moment caused by the 20 kN load about A, that will be force times distance. Now our force is 20 kN. So we have 20 kN, and then our D, or the perpendicular distance, will be 1 meter. Because again, our load forms a 90-degree angle with this particular line. And then this is the perpendicular distance from the load up to our point of interest. So this is times 1 meter. And then, sir, what will be the sign? Will it be positive or negative? Now since our rotation was, again, counterclockwise, our sign will be negative. Because again, counterclockwise movements will be negative, and then clockwise movements will be positive. And so let me just erase this one. Now what if you want to consider this vertical component? What will be the rotation? Again, try to imagine holding this point. Now, if you apply a downward force right here, our object will naturally rotate clockwise. And so if you want to see this in action, it will actually look like this. And so our body has rotated clockwise. Now sir, what will be that moment? If we are to calculate the moment of the 25 kN load, we have 25 and then kN multiplied by the perpendicular distance between the load and our point. And so that will be 6 meters. Because again, our line forms a 90-degree angle with this line. And so this is actually our moment arm, this distance. Because this is our force, and this is our point A. And so it will terminate at this point. And then this total distance is 6 meters. And so this is actually 6 meters. And then sir, what will be the sign? Will it be positive or negative? This is positive. Now this is because our body has rotated clockwise, as I illustrated earlier. And so let me just erase this one, and then let's try to consider the moment caused by this particular load. Now if you're holding this one, and then you'll pull this one to the right, because again, this is just along our line of action, our body will rotate counterclockwise. Now let me just clarify this one. Again, we can move our force at any point along its line of action. And so we can actually interpret this one as a pulling force right here or a pushing force right here. That will just be the same. And so let's continue. This will cause the body to rotate counterclockwise. And so the moment of this load will be 43.3 multiplied by the perpendicular distance. Now, the perpendicular distance will actually be this distance, because again, our force forms a 90-degree angle with the vertical, and so we need this vertical distance. Now sir, what is this distance? That will be 4 minus 1.2, and so we have 4 minus 1.2, that will give us 2.8, and then this is meters. And so again, this is kN, and then we will multiply this one by 2.8 meters. And so this will be our moment. And then sir, what will be the sign? The sign will be negative because this force has caused our body to rotate counterclockwise. And so take note of this one. And then sir, how about the 10 kN load? If we hold this one and then we'll apply this force, our body will rotate counterclockwise. And so our sign will actually be negative. And so our M will become negative 10 and then Kn multiplied by the perpendicular distance. Now since we have a horizontal force, this will be the 90-degree angle. And so this will be our perpendicular distance. Now that's 4 meters. And so this is times 4. And so we have negative 40 and then Knm. Now if we want to get the total moment about A, we have this equation. Now let's just call this one MA. Again, that will be negative 20 times 1, because again, this will cause a counterclockwise rotation. So minus 20 times 1, and then we have 25, and then times 6, which is plus because it will cause a clockwise rotation. And then we have minus 43.3 multiplied by, again, this is 2.8 meters, this distance. So we have 2.8 and then minus 10 kN multiplied by 4. And so this is actually negative 31.24. And then we have kNm. Again, the unit of a moment is always a unit of force multiplied by a unit of distance. That's what you have to remember. And so since I have discussed the concept of rotation, we will now solve the moment at B. And so we will actually hold this point. And so we have mb equal to, this force will cause a counterclockwise rotation about B. Because again, if you'll hold this one here, and then you will apply an upward force right here, our body will rotate counterclockwise. And so this is minus 20, and then times 1, and then we have this load, which is plus 25, and then multiplied by the moment arm, which is 6. So times 6. And then this is positive because if we apply a downward force here, our body will rotate clockwise. Now, let me also clarify this one. The direction of the force will not determine the sign of the moment. What will determine the sign of the moment is the rotation. Now, as you can notice, this is a downward force. However, the rotation it caused is clockwise. And so that's why this is positive. Now, most students have misconceptions about this one because once they see a downward force, they will automatically change this one into minus, which is wrong because again, we are interested in the rotation. And so let's just fast track. We have minus 43.3 and then multiplied by 1.2 because this is now our moment arm. I mean, this is actually plus because if we hold point B and then we'll apply this force right here, it will rotate our body clockwise. And then finally, we have the 10 kN load. Now, we have to remember this concept. If the line of action of our force hits the point of interest, then the moment it will cause will actually be 0. Now notice that the line of action of 10 kN will actually be this line. And so notice that this line of action directly hits point B. And so that means that the moment it will cause will be 0. Now if you want to think of it conceptually, if you will add this one, you have plus 10. And then what will be your moment arm? You will actually not have any moment arm because we don't have any perpendicular distance between point B and our force. Now most students will actually get this wrong because they will multiply 10 by 6 meters. But then again, you cannot multiply a force by the parallel distance because notice that 6 meters is actually parallel to 10 kN or this line. And so that's why 10 times 6 is actually wrong. And so let's just remove this one. If you want to write it in your solution, you just have plus 10 and then times 0 because again, there is an absence of a perpendicular distance. And so this will become 181 and then 0.96. And then our unit will be kNm. This is our answer. And then now, we will try to solve the moment at point C. And so we have this one. Now this is a bit challenging because our point is not right at the corners. However, the concept will still be the same. We will still multiply the forces by the moment arms. And so our MC will become, now let's just assume that this is at the center, so this is 0.5. And so we have minus 20 and then times 0.5. Again, this is minus because if you hold this point and then you apply this force, your body will rotate counterclockwise. And then we have plus 25 and then times the moment arm, which is this one, that will be 6 minus 0.5 because this is also 0.5. So we have this distance. 6 minus 0.5 will give us 5.5. And so this is 5.5. And then we have minus 43.3 multiplied by the moment arm. Now our moment arm will be this distance from here up to here. Now that will be, again, this is 2.8 meters because 4 minus 1.2. And so this distance is actually 2.8 minus 1.5. Now that will give us 1.3 meters. And so we have minus 43.3 multiplied by 1.3. Again, this is minus because this will cause our body to rotate counterclockwise. And then this is 1.3 because this is our perpendicular distance from the force up to our point. Now, if you're new to solving moments, just try to project a line from the point and then also project a line along the line of action of the force. And so it will be this line. And then try to check the perpendicular distance. Now, it's quite clear that this is the perpendicular distance if we consider this force. So try to remember that one. And then finally, we have minus 10 and then multiplied by 4 minus 1.5. And so we have 4 minus 1.5. Or you can also get the numerical value of this one. However, I'm just writing it here so that will differ from this solution in which we actually used the numerical value. Now this is also the same as 1.2 plus 1.3. And so let me just write this one here. You can also use 1.2 plus 1.3. It just depends on you. And so adding all of these together, we have 46.21 and then K&M. Now sir, what does it mean if we have a positive sign? That means that the net rotation will actually be clockwise. Now what if sir, this is a negative value? Then that would mean that the net rotation will be counterclockwise. And so this is what you have to remember. Whatever your answer is, just take note of the sign convention that you used. Now it will not matter if you'll assume negative as clockwise and then positive as counterclockwise, because the magnitude of the result will always be the same regardless of your assumption. Because if you will change this one into positive and then this one into negative and then this one into positive and then this one into positive, considering these assumptions, you will just get minus 46.21, which is just essentially the same value but opposite sign due to the assumption. However, let's just stick to my assumptions. I'm just showing this one for the purpose of discussion. Now, there's something wrong here because this is actually C. We will be solving D in our next question. And so let me just erase all of these. And then let's solve the moment about D. So we have MD is equal to plus 20 times the moment arm, which is 6 minus 1, which is essentially this distance. Now that will be 5 meters, so times 5. And then we also have minus 10 and then multiplied by 1.2. And then we'll actually exclude these forces because the line of action of this force directly hits point D and also the line of action of this force. Now recall that we initially had 50 kN and then inclined 30 degrees. Now notice that this force directly acts at point D. Now if a force directly acts at a certain point, then that will cause no rotation because essentially you won't have a moment arm for 25 kN and 43.3 kN. If you'll write that down, that will be plus 25 times 0 and then plus 43.3 times 0. And so these will just be neglected. And so adding these, we have 88 kNm. And so this is our answer. And so now, we'll try to solve this problem. Now this will be easy because we already discussed all the concepts. Now first, we will resolve these inclined forces into components. Now recall that if you have a force P and then this is, let's say, a 3, 4, 5 triangle, if you want to get the x component, you have Px is equal to P times the actual x component divided by the hypotenuse. And then if you want to get Py, you have P multiplied by the y component, which is 4 divided by 5. And so this is how you get the components. And so for this load, we will actually first get the hypotenuse. Now, the hypotenuse will just be square root of 1 squared plus 1 squared using the Pythagorean theorem. And so we have square root of 2. So this is actually square root of 2. And so now, we can resolve this into components. And so we have a vertical force here and a horizontal force here. Now take note that if you'll resolve a force into components, then you will consider the direction. Since this is pointing upward and then to the right, the component will be upward and acting toward the right. So this is F1x and this is F1y. Now our F1x will be 600, which is essentially P or the force considering this example, and then multiplied by the horizontal component, which is 1 divided by square root of 2. And so this will give us 424.26. So this is 424.26. And then our F1y will just be the same because again, our y component is also 1. So we have 600 and then times 1 over square root of 2. So we have 424.26. And then this is pounds and also this one. Now we have to determine the moments produced by each of the forces about point A. And then finally, we have to find the resultant moment. Now, the resultant moment is just the summation of all the moments. And so for F1, we have, let's say, the moment caused by F1 about A, we have 424.26 and then minus, because again, if you'll hold point A and then you'll apply an upward force, your body will rotate counterclockwise. And so we have minus 424.26 and then multiplied by the moment arm, which is the perpendicular distance. Now this is the perpendicular distance, which is 6 feet. And so we have 6 feet. Again, this is pounds. And then we also have F1x, which is still 424.26. However, this will cause a clockwise rotation about A. So this is plus and then 424.26 multiplied by the moment arm, which is 3 feet because this is the moment arm of our horizontal load. And so times 3. And so we have, let's just store this value into a. We have negative a and then times 6 and then plus a times 3. So we have negative 1272.79. So this is minus 1272.79 lb times feet. And so this will be our answer. And then if we want the moment of F2 about A, then we'll actually get the components. And so let me just erase this one. We still have vertical and horizontal components. However, since we are given the angle, we will just use cosine and sine. And then since this is with respect to the horizontal, we will just use cosine for the x component and then sine for the y component. And so this will be 750, and then since this is vertical, we will use sine and then 60 degrees. And then for the horizontal component, we have 750 and then cosine and then 60. So we have, let's just type this one. Our MF2A will be negative 750 sine 60 and then multiplied by the perpendicular distance, which is 6 plus 3 and then plus 3 because it's this distance. So that would be 12 feet. Or you can just write it as this one. And then the horizontal component of F2 would actually not cause a rotation about A because its line of action directly hits point A. And so this is our only moment. So we have negative 750 sine 60 and then multiplied by 12. So we have negative 7794.23. And then our unit is lb times feet. And then for MF3 about A, we still have to resolve this one into components. And so we have a vertical component which is 900 and then sine 30, and then we have a horizontal component which is 900 cosine 30. And so taking moments about A, we have plus 900 sine 30. Again, we are considering this one and then it will cause a clockwise rotation about A. And then the moment arm will be 6 plus 3, which is this distance. So that will be 9. And then we have minus 900 cos 30, which is the horizontal component. And then we will multiply that one with 3 feet, which is the perpendicular distance. So times 3. And then we have 900 sine 30 times 9 and then minus 900 cos 30 multiplied by 3. So we have 1711.73. And then this is lb times feet. Now, if you want to include the signs, this is counterclockwise since we have a negative answer, and this is also counterclockwise. However, this one will be clockwise since we have a positive answer. So this is clockwise. And so now to get the resultant moment, let's just label this one as MA. We will just add all of these. So we have negative 1272.79 minus 7794.23 and then plus 1711.73. So we have negative 7355.29. So minus 7355.29 and then lb feet. And so our resulting moment is actually counterclockwise. And so this will be our answer.